Okay, so let's do the magnetic moment of a hydrogen atom. So this is example. Right. So we can treat the hydrogen atom as a current loop, right? So we have our nucleus of our one proton, and then we have our electron orbiting our hydrogen atom, all right? Now, because it's in circular motion, it obviously needs a centripetal force to keep it in circular motion, right? And that force is the Coulomb potential, right? So we could write the centripetal force as this. Where this is a charge of E plus E, right? Because it's a proton. There's a charge of negative E. Just multiply it together, get the constants. And then R is the Bohr radius. And the Bohr radius is given to us as this. So it's about 0.5 angstroms. An angstrom is a tenth of a nanometer. So it's half of 1/10 of a nanometer. Right. Now, right, this is the force, and then for any circular motion, the centripetal acceleration is equal to the velocity of that object rotating around, rotating divided by the radius, r, right? And then from this, we can calculate the velocity. Right, this is the velocity of this solid for V over here, right? So we have the velocity. Now, what will we use this velocity for? I'll write down the value for the velocity. So it's actually traveling pretty fast, about 1,000 kilometers per second, or 2,000 kilometers per second, I should say. All right. Now, what we need to do is we want to find this quantity. All right. We want to find mu, and mu is equal to n times I times the area, right? And then n, of course, is just 1, right? Area is easy to calculate. The area is given by just the radius squared, right? The Bohr radius squared. And then we need to find the current. And that's why we calculated the velocity, right? What would be the current in this case, right? The current is how many charges pass you in a given amount of time. In our case, 1 second, right? And here we only have 1 charge, so we need to know how many times it passes us in 1 second. And what kind of quantity is that? If you think of like cyclic motion, right? This is rotating around and it's repeating the motion. So how many times something passes us, how many times this repeats this motion in 1 second is what? Open up the chat. Hertz, yes, it's the frequency, right? The frequency literally means, think of the word frequency. How often does something occur, right? This is the frequency, right? And the frequency is given by 1 over the period. The period is how long does it take for it to make one rotation, right? So the period, if we take the reciprocal of the period, we get the frequency, right? How long does it take it to rotate around here once? And then we could scale that up to the frequency by taking the reciprocal. So now we need the period. So how long does it take to travel around this circle, right? So the period is equal to the distance times velocity, right? The distance is just the circumference times the velocity. So we plug this in, and we get and we get 2 pi, I'm sorry, just write it down. Is equal R, and then if we bring this inside, we get square pi times e squared over epsilon naught times m. We get this for the period. Now we found the period, right? And we use this to calculate the current, right? It's just the charge times how many times it passes us in 1 second. So the current is given by E times the frequency, right? So do that, and then we get this. Right. Now we'll plug this into this formula. I'm just going to keep it as R for now, and we'll plug in the distances at the end. So now let's plug it in. All right. So that means the magnetic moment is I times A, which is just E squared epsilon naught times pi. Oh, wait. This should be 1 over, right? Because this is tau. So then the frequency is equal to 1 over this. I forgot to flip this over. Okay. Flip this. E squared epsilon m over pi E r squared. And then this is times 2 pi r. And then if we bring this inside, we find that this is, these two cancel out. And then this cancels out with one of those. And then what we'll get is this. Right? And we'll just left with this simple answer. And this ends up being E times, just make sure I got this right. And we had that 4 pi originally. Yeah, that's right. And this ends up being so negative 24th A times meters. And this is how we calculated the magnetic moment of a hydrogen atom, right? The tricky part here is figuring out the current, and we just calculate it based on the strict definition of current, how many charges you pass you in 1 second. If you look at one location, here it's just one electron passing us multiple times. We calculate how many times that electron passes us in 1 second, and then we can calculate our current and figure out the area. Any questions on this? So this magnetic field and the fact that it relies on this right-hand rule where the force is produced perpendicular to the B field and to the current allows us to do a lot of cool things with it, right? It allows us to really convert electrical energy into motion, right? We rely on this B field to convert this energy into actual motion. Because it's created perpendicular so that in essence we can have these rotating spindles that will never stop moving, right? We could convert it into circular motion because of the fact that the velocity is perpendicular to the force, right? So this allows us to create circular motion and cyclic motion, and allows us to really make these efficient devices, right? We don't use electrical, we don't convert motion with electrostatics, we do it with this B field. We also use it to convert electrical energy into sound energy, right? Speakers, right? And microphones. And speakers and microphones essentially work the same way. It's just that instead of, for speakers, you convert into the electrical energy, or the energy in the electromagnetic field, I should say, into mechanical motion of the air molecules, right? And with microphones, you're doing the opposite. You're converting the mechanical motion into an electrical signal. And I'll show you how it exactly works. So the way speakers work is you'll have a permanent magnet or an electromagnet, and this is one design that they show in the book. You have something like this, right? So this is the North Pole, this is the South Pole. So you can think of these as two of these horseshoe magnets put together, right? And then this is cylindrical, right? It rotates around. If you ever seen the base of a speaker, it's round, right? This is cylindrical. I'm just drawing a cross section. And there's a coil of wire connected to the cone of the speaker, which is what you normally think of as the speaker, right? And this cone, sorry, and it's this cone that moves up and down. And over here, we'll have a coil of wires. Right? And based on the strength of the current going through these wires, these speakers will experience a force either going up or down. Let's connect this to the speaker. These coils of wires are connected to the speaker, right? And based on the strength of the current, it'll move up or down, right? And what will happen is that when it moves up, let's say if it moves up, you'll get a bunching of the air molecules, right? Because the air molecules, it takes time for them to move. So the speaker moves rapidly up in a given amount of instant, it will create a bunching of these air molecules. And then when it moves back down, let's say if it happened already, it'll make a sort of vacuum where there was no air molecules before, and it'll stretch them out, right? And the air molecules become spaced out. And then you get this longitudinal compression wave, right? And this is just what sound is. And then over here, where at the other antinode, these become spaced out. Maybe I'll erase some. All right. So over here, the brown is when they move upwards and compress. The red is when when it expands and experiences decompression, right? And this is based on the sound signal, right? So if we send in, like let's say if we have a current and we send in an AC signal, right? Based on its frequency, this is in time, based on its frequency, right, which is just, if you look at the time, it's just, this is the frequency, right? I'm sorry, this is the period. Based on its period of frequency, we'll make different different tones, right? Because the tone is just the frequency of the sound wave or the wavelength, right? So we can convert it into electrical energy. And then if let's say if I talk into the speaker, right, me speaking into it will move this up and down naturally, right? And this will actually create a current in this wire, which is what we'll go into next, in the next chapter. Now, one last topic before we finish this section. Is the Hall effect, which is quite interesting. Now, the Hall effect is due to a moving charge. So let's say in a wire, if we look at it due to a microscopic effect in a wire. So let's say if we look at the wire very closely, right, and we apply a potential on the wire, right? This is the plus side of a battery, and well, let's say if we connect it to the battery, this is the negative side, right? So that the electrons, well, let's actually reverse it. I'm sorry, I'm used to thinking of the conventional current. Let's follow with this thing. So let's say if, let's say this is the negative side, this is the positive side. So this means the electrons in here will move in this direction, right? Opposite of how you think of the conventional current, how the conventional current moves, right? And they move at some drift velocity, right? The electrons scatter off of the atomic impurities in the sample, and they move at some drift velocity, right? I had you guys read the section because we were going through the whole update and everything. We didn't get to really go over the microscopic view of currents, but it's okay. We did go over a little bit actually, but so it's the drift velocity. So right now the current is moving in this direction. Now, if I apply a B field on this wire, what happens? Let's say if I apply a B field into the page, what will happen to these electrons? Anybody? It will cause these to have a velocity, a force, right? And based on the right-hand rule, let's figure out which direction the force is in, right? The charge is moving this way, right? Now the B field is into the page, which is, see that finger? It's into the page. And then for a positive charge, it would be up. But because these are negative electrons, the field is actually downward. I mean, the force is actually downward. So what would happen is that the velocity of these electrons would actually be downward, and they would start to move downward like this. Then what eventually happens is that you'll build up charge on one side of the wire. So after some time t, I'm just going to erase it. What will happen, right, we'll have our electrons. Initially, they're all throughout here, and they'll all start moving down, and then we'll have all the electrons on one side of the wire, or a majority of them, right? And now we have a buildup of negative charge on this side. So what happens is that this side is kept at a negative potential compared to this side. Right? And you could actually say that you have a plus and minus charge. On this, now, this is what's called the Hall effect. You build up a charge on one side of the wire compared to the other when you apply a magnetic field. And this induces a potential, right? And the equation relating it, right? When what will happen is that it'll build up the charge over here to balance out this magnetic field, right? Remember from that velocity selected that we talked about last time, where the force due to the magnetic field in one direction cancels out with the force due to the electric field of the capacitor, so that only a certain velocity of charge of a certain particle, a particle with a certain velocity goes through that velocity selector. So what will end up happening is that we'll build up a certain amount of charge so that the electrostatic field force due to the electrostatic field from the charge buildup cancels out with this magnetic force. So then we could say, remember Lorenz's law, right? For a charge, the full force on a charge is the charge times E plus VB. Right? Now, if this force is 0, right, we just get this relationship. Right? And then we get this. Right? And when we solve this, we'll end up getting the charge of the electron times the electric field, or the Hall EMF, right? This is, you can think of this EMF as, you can think of this charge distribution as an EMF, a source of electromotive force, right? Because we have a buildup of charge. It's similar to this, right? This charge, we could use this to operate another circuit, and that's correct, Danny. And we'll have this, what we call the Hall EMF. Oh, I'm sorry, not the Hall EMF, the Hall field. And this is equal to just E times the drift velocity times B, right? Because this is just the drift velocity. I'll fill it in over here now, right? And the drift velocity is perpendicular to the magnetic field. So they just become equal to each, it's just the multiplication. And then we get this. And then the Hall EMF, right? That's the potential. And for a capacitor, the potential for a capacitor right? V is just equal to E times D, right? It's just the electric field, it's uniform inside of here, times the distance between them, right? So then this just becomes E times D. And then using this equation, the charges cancel, the amount of charge cancels out, and we're just left with the velocity times v times d, right? Now, if you look, it's proportional to d, so that we could actually use this to measure the current going through a wire, right? By measuring the voltage across here. And there's many different uses that we could use this for. And that concludes this chapter. Now we'll start on chapter 28. Okay. So far we just talked about the forces due to a magnetic field. We didn't describe how to get a B field, right? We just said that a wire moving charge creates a B field, and this moving charge, because it creates a B field, it feels a force from another B field. We didn't actually describe the magnitude of the B field, either created by a charge or by a wire. And now we'll go into how to calculate the B field from different sources. All right. Okay. So first let's talk about a magnetic field due to a straight wire. So initially, when humans or scientists were first studying magnetic fields, they had no idea what this equation, how this equation worked, right? And at first, we empirically found the relationship of these these equations, and we did this by measuring the magnetic field at certain distances from the wire, and based on also the magnitude of this current. And what we found was that the B field was proportional to the current and inversely proportional to R. So that the further away you were, the lower the B field, the higher the current, the more charge you have, the higher the B field, right? And this explains these drawings, right? Now, to make this equal, we used a certain set of constants. We just said, okay, it's proportional to this, so we can make it equal by figuring out what this by setting this constant. Initially, we didn't understand these constants, but now we do, and we found that it's exactly equal to this constant mu naught over 2 pi times I over R. And mu naught is the magnetic permeability, or how much a magnetic field can go through a certain material. Right? It's very similar to the permittivity of an electric field. Slight differences, but it's very, very similar. You can think of it as the same thing. And here it's the permeability of free space, right? How much of a B field is created by this certain amount of current, and that's this far away. That's the permeability, right? This could have been easily a different quantity. And we didn't really understand this quantity until we understood that light was an electromagnetic wave. And it actually turns out the multiplication of the permeability and the permittivity will give you the speed of light, which was an amazing thing that was discovered by Maxwell. So now let's see how these forces exactly add up. And we'll go into driving it in hopefully by the end of today, if not Wednesday. So let's first think about how these forces, what happens with these forces. Now, imagine if I have another wire over here,